The loop and junction rule. So often you'll see these in a book saying it's called Kirchhoff's loop rule and Kirchhoff's junction rule, Kirchhoff's voltage rule, Kirchhoff's current rule, but whatever you want to call it. You call it what you want to call it, it's still physics. Okay, so let's just talk briefly about the important things we've looked at so far. The first is this one, the definition of electric current. So the current is the flow rate of charge. So it's change in charge over change in time. If I have a metal, then I can also determine the current based on the electric field. So you apply electric field in that material, and that gets charges to move with an average drift velocity. They speed up and slow down, speed up and slow down. And so I can say that current is equal to the value of the charge carrier. So if it's an electron, that'd be E. The charge carrier density, how many charges per unit volume. The cross-sectional area of the wire. U is the electron mobility, and E is electric field. Now there's another way to look at this property of metals that prevents charges from just moving infinitely fast, and that's resistance. So resistance is defined as the change in electric potential over some element divided by the current through that element, and it depends on some property of the element, resistivity, or you could do conductivity. The length of the thing, the longer it is, the more resistance it has, and the wider it is, the less resistance it has. And so these are just two ways of looking at the same thing. Okay, let's consider the simplest circuit that we could think of. Well, okay, second simplest. The simplest would just be a wire connected to a battery. Here's a battery, and this battery maintains a positive change in potential across it. That's what batteries do, and that would be, we call that an EMF. So this is a D-cell battery. The EMF would be 1.5 volts. That's just how alkaline batteries work. So this would make an electric field in here. And this thick wire is then hooked up to a thin wire. And then the thin wire is hooked back up to a thick wire, which is supposed to be the same, but I was not the best drawer. This is a light bulb. If you take an incandescent light bulb and connect it with two wires to a battery, that's exactly what you have. Where this part, the thinner wire, is the filament, the wire filament. So what happens in a light bulb, in an incandescent light bulb, is that the filament has a current, and the current makes that filament get hot. It gets so hot that it glows. Okay. But the important thing is we can use this as an example to apply the two rules, the loop and the junction rule. So here I have electric field in this wire, E1, and then I have an electric field in this wire, E2. I'll write it down here. That's A2 and L2 for the length and the area. This is a length of A1. And I'm breaking this as just one whole wire, even though it's in two pieces. So it has length L1, the whole thing. Okay, so let's first do the loop rule. This just says that the change in electric potential over a loop is equal to 0. This is another way to state that the electric field is conservative and why we can do an electric potential energy. The same thing could be true for gravity. If I take an object on the surface of the earth and I move it in any path and I get back to the same spot, then the change in gravitational potential energy is 0. So if I take an electron and move it around a loop, the change in electric potential energy is 0. I divide by the value of that charge, and the change in electric potential is 0. So that's what the loop rule says. It's really just a consequence of the work energy principle. Okay, so let's apply that in this particular case. In this case, if I go from here, one side of the battery, to the other side, what's my change in potential? It'd be EMF, or 1.5 volts. Now what about this part? If electric field is constant in the direction of the wire, then the electric potential drop along this first wire is just going to be minus E1 L1. And then I have this other wire, it has minus E2 L2. And that is equal to 0. So from that, I could possibly solve for a relationship between E1 and E2, but this is just setting up the loop rule. And I'll show you another case that's more complicated in just a second. Now, I also want to show you this other diagram. This is the same situation, just drawn in a different way. This is a circuit diagram. So in a circuit diagram, this is the battery. Those are the same things. And so we draw a long line to represent the positive side of the battery and the short line for the negative side. And then this is the resistor, which is this over here. So in this case, I would want to consider this in terms of the electric current. And I can write the loop rule as, again, this is EMF. And then the voltage drop along this is just going to be equal to I times R. So this way would be EMF minus IR equals 0. And I'll do another example that's more complicated. But I want to show you, this is just an introduction to the loop rule. I'm going to do another problem where we start getting into this, and I'm actually going to do it both ways so that we can see how that works. But I just want to introduce you to the loop rule. Let me show you a more complicated loop rule. And I'm going to draw this as a circuit diagram just because it's easier. There's a reason that we have those. Okay, so here I have EMF, and I have 3 resistors. So let's call this R1, let's call this an R2, and let's call this R3. Now, this is obviously a much more complicated circuit, but you can imagine the battery being connected to a light bulb or something, and then these are 2 light bulbs connected in this weirder pattern that we'll talk about later. But if I want to do the loop rule, so I can say, let's call this a current I1. Let's call this current, let's say the current comes down here, and then I have a current I2, and the current comes through there, I3. So the loop rule says that no matter what loop I take, the changes in potential should be 0. So if I start from this point right here and go this way, I'm going to go this way. Let's draw this out. I'm going to go this way. I'm going to go like that. So if I do that, I would have EMF. Now, the voltage drop along a resistor is, since you're going in the direction of the current, which is the direction of the electric field, it'd be a negative drop in potential. So I get negative I1 R1. And then over here, I'm going in the same direction as I3, so it'd be minus I3 R3. Oh, that's a B. R3 equals 0. Now, I could also do this loop. Go down here, I could go through the bottom. And if I did that, I'd get EMF minus I1 R1 minus I2 R2 equals 0. And finally, there is one other loop I can do. I could go from here this way. Now, notice up here, if I went the other way, I would just change the signs of these, but now I would change the sign of that too. So everything would be multiplied by -1 and it'd still be equal to 0, so that would work. But if I start right here and I start at this point, if I go across this resistor in the opposite direction of the current, I get plus I3 R3. And then I'm going in the direction of I2, so it'd be minus I2 R2. And so these are a series of equations. They're actually not enough to solve for everything, but in this case, I don't know. I could possibly not know the 3 currents, and I have 3 equations, but they're not 3 independent equations. I only actually have 2 independent equations. Okay, but that's an example of the loop rule. And again, I'm going to do another problem with this. Now let's look at the junction rule. Let's take that piece of my circuit before. So here I have an electric field E1, and this is the thinner part, and I have an electric field in here E2. So if current is the flow of charge, then at this point, the flow rate has to be the same as at this point. If it's not, then the amount of current coming into that point would be different than the amount of point charge leaving that point, and so I'd get a charge buildup right here, which I don't get. So the only way for this to be not get a charge buildup is I1 and I2 have to be the same. You can think of this as a pipe. If this was a pipe of water, then the flow rate in this part, how much kilograms per second passes through here would have to be the same for the two parts, or you'd get water buildup or water depletion here, which doesn't happen. Now, in order for that water example to work, the water over here would have to go much faster than the water over here, but still the flow rate is the same. The kilograms per second is the same. And the same is true here. The drift velocities are not the same. The flow rates are the same. Okay, so the current I1 has to be equal to the current at I2. And this is the junction rule. So if you want to write this out as our other model, I could say Q in A1 U E1 equals Q in A2 U E2. Those are the two expressions for the current. They have the same charge density, charge carrier value, electron mobility, so I just get A1 E1 equals A2 E2. And this says that since this has a much bigger cross-sectional area, it's going to have a much smaller electric, this is a smaller electric cross-sectional area, it's going to have a much higher electric field and therefore a much higher drift velocity. So it is a lot like that whole water flowing through a pipe model. Okay, but this is not a very good junction rule because it's almost too obvious. What about something like right here? What about the current coming into this junction? A junction is where two or more wires meet together. Here, two wires are meeting together. Here, three wires are meeting together. So the junction rule says that the total amount of current coming into the node has to be equal to the current leaving the node. Otherwise, you'd have a charge buildup. So in this case, I'd get I1 equals I2 plus I3. And that's for this up here. Okay, right there. And so actually with this equation and the two of these other equations, I now actually have enough to completely solve for the system, which I will do later if I know the values of the resistors. Okay, there's another node right here, and this says that the current coming in would be I3 plus I2, and that'd be the current leaving, which is I1, and it's the same equation. Okay, and there'll be some cases where you don't know which direction the current is moving, and you just pick, and that's fine. And if that's the case, when you solve for the thing at the end, you'll get a negative current. It just means you got the direction wrong. So that is an introduction to the loop and junction rule. I will do a problem like this next.